what Salesforce.com is. Mostly we're known from our sales product. And we've had our sales product since we started. It's called Sales Cloud. It's up there in the upper left-hand corner. But it's built on top of a platform. And that platform allows anybody to develop cloud-based applications. So we use it to develop cloud-based applications. We opened it up to the world about 5 years ago. It's called the Force.com platform. And it contains everything you need to develop full-fledged business applications. So we've done that with Sales Cloud, and we've done that with Service Cloud. Sales Cloud is used to manage all your sales information. Service Cloud is used to manage the customer service and support information. And then there's a Custom Cloud, which is a set of applications that people have written on their own. And to date, we have around 72,000 customers and over 150,000 custom apps. And then I have Collaboration Cloud shown up there. Collaboration Cloud is a new product called Chatter, which you may have heard about. It basically enables social networking within the enterprise. And I'll be talking more about that. And the tools for doing that are actually enabled throughout the platform. So every application built on Salesforce now is social networking. Search's responsibility is to handle all of this. So we manage search. So we manage indexing the data and querying the data for everything in the platform. For the sales application, the Service Cloud application, the custom applications, and Chatter. Operational difficulties. Okay. So that means we've got a lot of data. How much data do we have? We have about 8 terabytes right now, and it's a lot of volume. So on a given day, you'll see that we've grown to about over 600 million indexing events a day. And by indexing event, I mean batches that we're indexing. Batches can be thousands of documents. And the requirements we have for performance is we try to get all of our index events to be available for querying within 3 minutes. We're successful at that about 90% of the time. In order to scale, we use a multi-tenant architecture, so I'm going to go over that before I dig into what search actually looks like. So what is multi-tenancy? Multi-tenancy is basically like everybody lives in an apartment building. Okay? And a tenant is an organization, what we call a board. So one of our customers is a tenant. And if you look at the database tables, rows are interspersed from org to org. Now, search doesn't exactly work like that, and I'll talk about that. Each org has users. There can be from one user to hundreds of thousands of users, and a given username maps uniquely to a single org. There's a lot of advantages to using multi-tenant infrastructure. One is that you make one code base to support. So you make a change, all of your customers get it. It also means that it scales well for ops. So we have, as I showed here, 680,000 plus custom objects, each of which is a separate table. We have 16 different production instances, and we only have 8 EAs. So when we do multi-tenant architecture, as I talked about yesterday at the panel, we don't just store everything in one big data center and go. We actually have a fixed footprint that we abide by, that we call a pod. And then we have multiple pods. And in order to scale out, we'll just create a new pod. And a single pod will hold a large number of customers. And those are shown up here in that row. So NA1, they have names like NA1, NA2, NA3. Those are in North America, as you can imagine. EMEA, we have AP0 and AP1 now, and we have a lot of other pods as well. A given pod has everything you need in order to service any request a customer might want to have service. So it includes load balancers to app servers, our Oracle rack, our search tier, the SAN, which is where indexes are held and where the database is stored, and then a bunch of other things that I'm not going to get into today. But it's worth noticing that one of them is a content management system. I'll actually be referring back to that a little bit. What I'd really like to do is to focus on what's directly relevant for search. So what happens in a pod where search is concerned? What happens if we blow up that picture a little bit? Well, we've got app servers, and we've got the Oracle rack. We have a query tier, and you'll notice there's multiple query servers there. An indexing tier with a single primary indexer, and then a secondary indexer, and I'll get into what the distinction is in a moment. And then the SAN, and backups are made from the SAN in a large object store that we've created called FileForce. It's worth noting that in our deployment, we started using Lucene back in 2002 with version 101B. Right now we're on 2.2, which is kind of an old version, and we're currently working through an upgrade to 2.9 and then Topatron, so we're hoping to be on 4.x by next year. Now let me go through what the steps are when we actually index a document. A request comes in, either because a user has typed something in or because it's been triggered through the API, and it changes some data in the database. That activates triggers on the database, and that data gets queued in an indexing queue. The other way things can get queued is through the secondary indexer. This is a system that allows us to re-index words from scratch offline. And we can do that continuously, both to make sure that things are in a good state and also in order to affect index format changes. How each object in the database gets indexed is defined by that object. And then we turn it into a searchable document and write it to the SAN. And when we do that, there's a couple of things that we do. One is that we don't index fields separately right now. We're indexing everything as a bag of words into a single field in order to improve search performance. As well, we also do n-gramming for tokens so that we can improve query performance for phrase queries. The indexer is connected to the SAN using single writer QFS. The query tier is connected using multi-writer QFS. And a typical instance, a typical pod will have about 1 terabyte of storage for the index. So now I want to get into what our indexing queues actually do. This is the picture that I drew in the last slide. I showed the Oracle rack connecting to the indexer that was hanging out over here, and the secondary indexer pointing to the indexer. That's actually not exactly what happens. The indexer is actually drawing its work from the database. So I want to talk about what this actually looks like. And note that we have a single indexer, but there are multiple VMs, multiple data VMs. And so what I'm going to be describing here is what happens on a single data VM. So actually what happens is the secondary indexer and the database both write into these tables that represent a priority queue. We have an incremental indexing queue, an offload queue, and a bulk indexing queue. And when there are changes in the database, these are incremental changes, those records get queued into the incremental queue, which is high priority. When we re-index words from scratch on the secondary indexer, they get enabled in the bulk queue. The primary indexer then picks up work out of these queues. And it's working on the incremental queue with a higher priority than the bulk queue, but it will work on both at the same time. So we have multiple threads that are devoted to each of the queues, more threads for the incremental queue, fewer for the offload, and fewest for the bulk queue. And they'll share as needed in order to maintain the proper priority. Now when the indexer gets to an incremental queue item that has a lot of records, it doesn't want to block everybody behind it. And that's what the offload queue is for. And then it continues working. So now I want to talk about our sharding strategy. So when the indexer writes to the SAN, what kind of indexes is it writing? So the first thing I want to say is that every word gets its own set of shards. So that's a way in which it's different from how the database operates. In the database, like I said, tables are kind of all mushed together. There's not separate tables for different words. But for the index, it makes sense. It's much easier to maintain a separate set of shards for every word. Now, our original sharding scheme had it so that whenever the indexer wanted to index a document, it would add it to whatever the smallest shard is. And shards were limited in size, so once it got to the limit, we create a new shard, and new documents would get added to that. We deleted records from an old shard, and then when that shard got optimized and it was smaller, then we might add records into that. Now, this was fine for indexing. It's pretty easy. And it's pretty easy for querying, but it's not very efficient for querying. So if you're looking for an account called John Smith, you don't know what shard this is going to be in, so you have to query everywhere. That's kind of inefficient. And that can be a problem in terms of resource utilization of the system. When you look at the number of user queries we have, you can see it's increasing linearly every year. And right now, we get about 7 million user queries every day. And that includes API queries. Well, if that's increasing linearly over time, and the amount of data we have is increasing linearly over time, and therefore the number of shards we have is increasing linearly over time, then not surprising that the number of partition queries is going to increase exponentially. Now, what I'm going to describe here doesn't get rid of that problem. I think there's no getting around the fact that as you grow, you're going to increase, and it's going to increase as a product of the number of queries you have and the amount of data you have. But we can do things to ameliorate it. And actually, I showed down here, we really shoot for having a very low average partition query time. So partition query means to query one of the shards. So right now, our median partition query time is about 100 milliseconds. We'd like to drop that, and 95% of them are happening in less than half a second. So what do we do? Well, the next step was shard by object type. So here what I showed was that everything was all mixed together, and we needed to search for John Smith, the account. You have to search everywhere. But what we did instead was we changed it so that we're sharding by object type. So if there are enough records within an object to warrant its own shard, we give it to them. So here you can see we have a shard for accounts, and a shard for account activities, accounts, there's 3 of them, contacts, opportunities, and leads. There's not enough for their own shard, so they share one. We still index into the smallest shard, but only for the smallest shard within the object type that we're interested in. So if you're indexing an account, you'll index into this little guy down here, but if you're indexing an activity, it'll go into one of these, or we'll have to create a new shard for John. Now if you query for accounts, you'll see you're able to query a small number of records. And this had a profound impact on the performance of our queries here. So this is a typical day where we're getting up to around 35% utilization on one of our query hosts. And this is before sharding by object type. And this is the week after we moved, this is before sharding by object type, so this was size-based. This is the week after we moved to sharding by object type, and seed utilization on that host was down to around somewhere between 5 and 10%. That's typical. Well, that's fine for querying, but we still had issues with indexing. With indexing, whenever you add a record to a shard, you have to find out where else it lived, so you can delete the old version. That shouldn't be so expensive, but in order to constrain our resources and make sure that we weren't killing our tier with that query, we had a limited number of threads we could use to allocate towards it. Now, we could have expanded that thread pool, that would have impacted performance elsewhere. So what we decided to do was to get rid of that long leg, and this is actually an illustration of having indexed in order from scratch. Each of these points in the horizontal axis is a batch that got indexed. And the vertical axis is how much time it took to index that batch. You can see most of the time is spent in this yellow region, which is deletes. That's pretty bad. In order to ameliorate that, we kept our object-based sharding, but now we're going to shard within that by record ID. That allows us to identify a specific shard for a given document when you index it. So the old sharding scheme that I described, if you're indexing an account, just add it to the small account. But now, if you're indexing an account, you'll figure out what shard it should belong in, and you'll index it to that one. that means that you know exactly where you need to look in order to delete it. That's all I want to say about indexing right now. Let's move on to querying. So when a user queries, it's like a query in a search box that goes to the app servers. And the first thing we do is do some query reformulation. I just want to mention these quickly. The first thing we do is to eliminate stop words in the query. Then we do some stemming and limmatization. And I know it's unusual that we would do both stemming and limmatization. There's actually a reason for that, which is for legacy purposes, which is we've always done stemming. And we have a lot of integrations with a lot of different products, and they've all used stemming. And as you know, once you index something in a certain format, you're going to want to query in that format. So if we stemmed it when we index, we're going to be stemming when we're querying. But in the last year, we're starting to roll out limmatization, and we can only limitize things that we can easily re-index right now, or that are new. So that's why we're using both. And that secondary indexing system that I described will allow us to change the index format for all words at once and coordinate querying with the change in index format. But we're not there yet. Once we are, that'll change everything for limmatization. We allow customers to define synonyms. So we have an admin UI where they can go in and say sofa, same as divan, same as couch, same as whatever. So that gets injected at query time. And then we also do proximity boosting. And we do that fairly crudely by basically taking 3+ term queries and creating different groups of phrase queries and boosting them appropriately. We can do better than that, but that's what we're doing right now. And that gets optimized using the end-to-end I described earlier. So now that we've reformulated the query, we're going to distribute the partition queries out to the query hosts to query the different charts and then aggregate the results back. When we distribute, so first the app servers are going to come up with all the different partition queries, and we maintain note affinity between the shards and the query hosts that are serving them. That lets us leverage file system capture. We also have throttling on the query hosts and the app servers in order to protect the query tier and also to ensure fairness between orgs. Because some orgs are going to have a ton of shards. Some orgs are going to have one shard. We don't want the ones with a ton of shards to overwhelm queries to the ones that have a single shard. And finally, when we do collect the results on the query hosts, we aren't always able to collect all of the results, because there might be many millions of hits, and we don't want to send all those back. So we bucket by record type to make sure we get representatives from each of the different kinds of objects that somebody's querying for. And finally, when the results get aggregated back to the app server before the return to the user, we do some post-filtering in the database. The first thing we do is record authorization and field level filtering. Now, it's unfortunate that we have to do this in the database after we query the search tier. And probably my biggest mission over the next year or two is to get rid of that. The reason why we do that, so sharing is our authorization models, that's what we call it. Our sharing rules are very complex. They've grown up over about a decade of different ways that users want to be able to control authorization in their orgs. And it's hard for that system to materialize a view that we easily index as atlas and index, and they constrain with queries. So right now we use post-filtering. That's fairly expensive, which is why we have to limit the number of records that we're getting back from the query tier. As well, I described how we indexed all the tokens from the different columns into a single field to improve query performance. But that means if you want to know, okay, I'm searching for dog, but I only want dog where the account name is Bob. So there we're trying to limit it to a single field. We haven't indexed single fields. So in order to do that, we're doing that constraint against the database. It's fairly cheap, as it turns out, because of the number of records that you're at that point. But still, an improvement we've been We also do some re-ranking of the results page that the person's looking at by last activity or last update, things like that. It's dynamic. Again, that can be pushed into the index. This is a lot simpler and actually gets us 90% of where we want to be. We also query the MRU. So there's a list of records that the person has referred to recently, and if those have been updated since, it's possible that those have been updated since between right now and when the last index time was. So like I said, our lag is around 90% of our records get indexed within 3 minutes. That means that 10% of our records in those 3 minutes aren't going to show up when you do a query. And there's obviously a tail that gets shorter and shorter. To bridge that gap, we query the database. We query the MRU and store the database. Okay, is that pretty clear to everybody? That's the basics that I'm going to go over, and then I'm going to go on to the next thing, which is the architecture. Okay, yeah.
One question. You said you have multiple queues and multiple threads running for the index.
Yeah.
That would update coherency.
A lot. We use locks in the database. So each org, we lock each org as we do an update, and we can also lock by record type if they're going to be in separate shards. So we just make sure they're basically the same thing twice into the same shard at the same time.
Okay.
So I many people saying that NFS is bad for performance.
What is bad for performance?
NFS?
NFS.
Yeah. Can you comment on that?
Yeah. I'm glad you asked. Actually, I'm going to get into that. I'll tell you what we did. NFS isn't really, I mean, at least in our case, if you're getting a cache, it's incredibly fast. We don't have a problem with that. But if there's a cache miss, first of all, it takes 30, it can take, depending on your settings, 30 seconds to get coherency between what's actually changed on your disk and what's available through the NFS cache. And with a miss, it can take a while to go to disk. So you're going to have some cost there for cache misses, but you can't really, I mean, you can do better maybe locally, but even then you're still going to have cost for cache misses. So let me actually get to that right now. So one thing I want to emphasize is, like I said before, we have a lot of data. We not only have a lot of data now because of this stuff, which is all of our sort of older stuff this lock is supposed to represent. This is kind of a avant-garde representation of everything we're trying to index. Basically, everything here is everything that involves authorization rules. So our sales product, our service and support product, but we also have other things that we're trying to index, and the volume of those things is going to get very big, very fast. So we have chatter. People are using it a lot. It's new, and it's getting really widely adopted. It's getting aggressively adopted. There's a cold storage system that we're writing that we're going to be piloting soon, and that actually is going to be shoving a tremendous amount of stuff into search. And then we have on our roadmap to make emails a first-class object, which is also going to create tremendous volume. And this is only sampling some of the stuff coming down the road. So we have pretty large scaling than we are now. As I said yesterday in the panel, I really try to make sure that we're designing for 2 years down the road. And 2 years down the road is looking pretty intense right now. So that's the amount of stuff we have to query. The amount of stuff we have to store, but also with every query, we're putting much more load in our system now than we were even a month ago. So in the last release, which just rolled out last weekend, and also tonight, we're starting what's called global search. This is a pretty horrible snapshot of it. This is like sort of mock-up before we actually have the product, but I have snapshots of what it actually looks like now later. Basically, there's a search box up here, and when you do a search, not only are you searching your standard CRM products, your CRM objects, or your custom objects that are in your custom app, but all the different applications that are deployed on the platform that you have access to. You can obviously limit the scope if you want. So the ones that are circled here, articles that service and support, content, this is the content management system I referred to earlier, and there's others. that means that we're doing a lot more querying, and by default, if you have your scope totally open, you're going to be querying all the objects that we've done such a careful job of segmenting into their shards. Okay. So this is to describe a little bit about what our next architecture is going to look like. That's going to help with this. I don't think it will solve the problem, but I think it's the right next step. It'll get us to where we need to be for what's coming down the road, which is, as you know right now, like I said, query servers talk through NFS to the SAM. And we actually don't have a problem with NFS when there are caches. Cache misses are very expensive. The indexer, there's a single indexer, because this is single writer QFS. And multi-writer QFS is a little weak, so it's high risk, we'd rather not use it. And finally, we're storing everything on a SAM, which is really expensive. So as we're getting more and more data, we don't want to store everything on the SAM. So here's what we're doing. We're getting rid of the NFS, and we're getting rid of the SAM. So when the indexers pull work off of the work queues, it can do it in parallel with multiple indexers. And those indexers are going to write locally and then push the indexes to the query servers. So they'll be querying locally. As well, we're going to have an additional cache layer between the local disk and RAM that's going to be solid state or improve performance for cache misses. Okay. So that describes some of the changes that we're making in infrastructure. But at the same time, we're getting innovations in the platform that we need to push into search as innovations for search experience. And we're just starting here. So actually what I'm going to paint is more of the challenges ahead of us and the opportunities for innovation. Is that 10 minutes or 5 minutes? Okay, well, let me breeze through this as fast as I can. Does that include time for questions? Okay, well, let me move through this really fast. The main thing I want to say, I don't need to do a lot of marketing here. Basically, chatter is a big deal. It represents what our CEO is calling the Facebook imperative, which is he founded the company about a little more than 10 years ago, and with the question, Amazon's really cool. Why doesn't every enterprise application look like Amazon? Why doesn't everything work through the web and be complex enough to support all the business needs? Well, now he's looking at Facebook, and he's asking the same question. This is an answer for that for the enterprise. Now, on Twitter, you can follow people, but here you can follow people, and you can follow data. It's had a pretty profound impact on how people are interacting with their system. So this is an account record, account owner, account name, all the standard stuff that people have used in the past. But now you have a feed on top of it. You can write something there, like this person says, on this account record. So they're not commenting on somebody's wall. They're commenting basically on the wall associated with this object. And they're saying, I'm going to meet with the CEO. Anybody have any help for me? And this person can post a file, which is the org chart. And they say, here you go. Because this person's following this account. So people are following the data, people are commenting on the data and interacting through the data. I'm not going to go through what the UI looks like, I think you get the idea. You've got your personal feed that includes people's status updates as well as things that happen on those objects that you're following. And when you search, right now we're splitting the record results into a separate page from the feed results, which isn't that great. So this is an area where the opportunity to really innovate, or this is the right way to go. Is there a right way to integrate the enterprise data with the social data? Nobody's really tried to do this before, at least in a way that I think has been successful. So this is really where we're going next. As well, we want to be able to leverage these social relationships to improve relevancy. So there's a lot of future work ahead of us. I'm going to skip the service class stuff. Bottom line, we really focused on structured data in the past. Now we have to deal with unstructured data. This is a pretty new application for us. And that poses different problems, specifically around relevancy, which is not that hard a problem when you have structured data. And as you all know, that's a much bigger problem when you have unstructured data. So we have to put a lot of attention there. One thing I've done to do that is we've created a new relevancy team. We built up the infrastructure team, we built up the features team. Bottom line, I think that we'll probably get from all of this is that we're growing a lot fast. 18 months ago, I had 1 team, 4 developers. Right now, we've got 3 teams, actually now more than 13 developers. And we don't really have a limit where we have to stop except where the teams are functioning well. these teams have gelled really well. Growing them has we found it to be really easy. So that's what we're doing now. And specifically, actually, shameless plug, we're actually looking for people with really solid Lucene experience. Committer would be great. And actually somebody who we can grow into committer would also be great. Our goal is not just to have, I mean, we've been using Lucene for like almost as long as it's been around, since it was a source code project. But we haven't done a lot to commit back to it, and that's something I'd like to see change. And one of my goals is to be able to enable developers to commit into Lucene, even working on projects that aren't on the core edition for Salesforce. So anyway, that's my contact